Welcome to the first class video of a very unique online offering of separation and mass transfer operations. In this video I'll give an introduction and overview of the course topic. But first, allow me to reintroduce myself. Many of you know me already from taking my material and energy balance courses a few semesters ago, or my phase equilibria class this past summer. But for those of you who have never met me, please feel free to address me by my first name, which is VJ. If you'd rather call me Dr. Toko, that's fine too. This will be my 7th semester of teaching in the Department of Chemical Engineering at the University of Florida, and 5th semester teaching ECH4403. Some other information and fun facts about me. My hometown is a small suburb in the Metro Detroit area called Fraser. I graduated undergrad in chemical engineering at Michigan in 2012, then came to Florida for my PhD, where I finished in 2018. My family consists of my wife Tara and 2 poodles, 8-year-old Puddles and 3-year-old Wally. In my spare time, I enjoy golf and gardening. This summer, I also started a new hobby of stand-up paddleboarding, which will hopefully distract me from the void of no Michigan football this fall. So, ECH4403. Let's start with the title of the course. It's a little strange. What do you think of when you hear the word separations? I remember my first day of SEPs in my class at Michigan, and I remember walking into class wondering if we were going to be learning about how to pick out the cherry-flavored jelly beans from an assorted handful, or twisting an Oreo to separate the chocolate wafer from the cream filling. Of course, these aren't applications that interest chemical engineers. Rather, when I say separation, I'm referring to methods that change the composition of a mixture. Some reasons why you'd want to do this as a chemical engineer include purifying the desired product of a chemical process. If you've seen the TV show Breaking Bad, you know that the protagonist was a talented chemistry teacher named Walter White, who built his business based on the quality and purity of his product. Some parts of the show alluded to the purification process that he used, which is an example of a separation process. Another application is purifying drinking water, which continues to be an ongoing problem in many countries in the world that need safe, cheap, and fast ways to clean their drinking water. Yet another somewhat classical example is in oil refining to make gasoline. Shown here on the slide are 6 samples of crude oil. The variation in color reflects the fact that each one has a different chemical composition. There are hundreds, if not thousands, of types of molecules in crude oil. So consider how a chemical engineer might isolate only the ones that are good in gasoline, like paraffins and aromatics, while excluding the ones that are not desirable in gasoline, such as asphaltenes. One last example that I think about every time I visit the grocery store are the various types of milk. There's pretty much an entire spectrum of options when it comes to how much fat you want, from skim to 0.5% to 2% to whole. Then you've got variants like organic, and to be honest with you, I'm not even sure what that means, and lactose-free milk. Now, of course, milk only comes in one form out of the cow, so how can a chemical engineer come in and remove only the lactose from or a specific amount of fat from the milk? Hopefully these are examples that have piqued your interest and demonstrate how common, ubiquitous, and important separation processes are. The main challenge associated with separation processes is that they don't happen spontaneously. In contrast, the opposite process is mixing, which we know happens naturally, and therefore is comparatively easy, and is why we don't have a chemical engineering class called mixing process operations. Although, just parenthetically, we probably should have a class like this because mixing has some nuance to it as well. And there are ways you can increase or optimize the efficiency of your mixing as well. So said another way, the natural order of the universe will always resist a separation process because a mixture is disorderly and therefore entropically favorable. In order to separate the components, you have to overcome the decrease in entropy that would otherwise occur. The way to accomplish this is to identify a characteristic difference between your components, then devise a way to exploit it. Here's an extremely fascinating example from the agricultural industry. When farmers harvest tomatoes, they don't distinguish ripe from unripe. How then do they get sorted before arriving at the grocery store? We know from experience that ripe and unripe tomatoes are roughly the same size, but ripe tomatoes are red and unripe tomatoes are green. Therefore, we have our characteristic difference, the color. The next step is figuring out how to use this in our separation process. In the old days, farmers would need to go through their entire crop relying on their eyes. This is, of course, very time-consuming and therefore expensive. Modern farming technology, however, has a machine that can detect the green tomatoes and knock them out. This clip I'm showing is from YouTube, which you can find just by searching tomato color sorting machine. While I find this tomato example incredibly fascinating, this is not very common at all in chemical engineering. In fact, chemical engineers are almost always dealing with molecular mixtures. Consider instead a beaker filled with water and ethanol in a 50-50 mixture. Say you wanted to separate the water molecules from the ethanol molecules in order to make pure water and pure ethanol. You couldn't separate this mixture by hand, even if you wanted to. You can't pick out single molecules of water or single molecules of ethanol. So what other possibilities exist? You could start by listing the molecular properties to try and find one that is different between water and ethanol. One example of a property that's different, you may find that many properties are actually different, is the molecular weight. For water it's 18 grams per mole, and for ethanol it's 46 grams per mole. While this is true, there's no way to exploit this difference. So unfortunately, this is a dead end, and you have to go back to the start and keep thinking. What other differences can you think of that exist between water and ethanol that are exploitable? Any two given chemicals are likely to have a difference in boiling point, and this is an exploitable difference by heating or cooling the mixture to a temperature that is between the boiling points. In theory, the chemical with the higher boiling point should remain a liquid, and the one with the lower boiling point should vaporize. However, we know from phase equilibria that the separation is not quite that clean. There are laws of thermodynamics that we must obey. Regardless, this exploitable difference of boiling point forms the basis of distillation, which is a process that forms a second phase by the addition of heat. So for a liquid mixture, for example, if you boil a portion of this mixture, you will form a vapor phase, and a vapor is very easy to separate from a liquid. You can simply drain the liquid out or allow the vapor phase to float off of the top, and therefore you've separated them. And if you require that the vapor phase comes back into a liquid phase, you could just condense it later. We will spend a considerable amount of time this semester learning how to design distillation columns, because this is perhaps the most ubiquitous separation operation that exists in chemical engineering industry. That is, deciding how large a column needs to be, what specifications it should have, and how much it will cost to build and operate. Going back to the crude oil example for a moment, distillation is the usual separation technique that is used in refining. This is a grossly oversimplified process flow diagram of how it works. As you can see, the bottom of the column operates the hottest, and the column gets cooler as you go up. Accordingly, components with the lowest boiling points keep rising up the column. Vapors are less dense than liquids, so they float upwards, while the higher boiling components stay near the bottom. On the right are some photographs of real-life distillation columns in chemical plants. In the second third of the semester, we'll shift our focus to absorption and stripping, which are closely related processes that you usually see in the context of cleaning a stream from a hazardous or valuable trace impurity in a stream. Here we are exploiting a difference in the chemicals' affinity for one another, and bringing a mixture of chemicals in one phase, vapor for example, in contact with another phase, liquid for example, can induce mass transfer of one of the components from one phase to the other. Finally, we will discuss liquid-liquid extraction, which is similar in principle to absorption and stripping, except there are two liquid phases involved, which are immiscible. Each of these three separation techniques may be classified as an equilibrium-based separation, which is firmly rooted in phase equilibria, a course you are taking right now or a course you have taken previously. As is the case with any field of chemical engineering, material and energy balances remain at the center of everything. I'd like to conclude this first video by briefly mentioning some topics that we do not cover in ECH4403. While these separation techniques are indeed important in chemical engineering, we don't cover these in detail because we simply don't have the time in a single semester. Additionally, some of these separation techniques are somewhat straightforward and easy to learn as needed. Magnetism, for example, is an example of such a straightforward technique. Either something is attracted by a magnet or it is not. There is no mathematical theory behind that. Similarly to filtration, or sieving is another example. If a molecule is small enough to pass through the sieve or the filter, it will pass through. If not, it will not. Now, some of these topics may be interesting to you, and that is great because at the end of the semester you'll be assigned a team project to choose a separation topic of interest and teach it to the class in a 15-minute presentation. More details will be given about this project when I assign it later in the semester, but for now I will wrap up the first video. Thanks for watching.